Hi student, Assalamu alaikum rahmatullahi wa barakatuhu. In this video, I shall explain the ligand field theory. Ligand field theory describes the electronic structure of transition metal complex. It mainly explains the effect of ligand. Molecular orbital theory explains the covalent character in a transition metal complex. Crystal field theory explains the electrostatic attraction in a transition metal complex, but ligand field theory explains both character, that is ionic character as well as covalent character of transition metal complex. First, what is complex? Complex is a product which is obtained from the combination of metal atom with a ligand. As we know that metal atom or metal ion is an electronic deficient atom. So it accepts electron from ligand and act as a Lewis acid. Ligand are those chemical species which can donate electron to metal atom or ion and act as a Lewis base. We represent the complex from an arrow whose head is toward metal atom and tail is toward ligand. Now, today I will explain the octahedral complex according to ligand field theory. Imagine 6 ligands approaching the pre-metal ion to form an octahedral ligand field. Thus, as we know that the central metal cation of 3D series element contain in all of 9 valence shell atomic orbital, which are this is the first row of transition series 3D1 scandium, 3D2 titanium, 3D3 vanadium, 3D4 chromium, 3D5 manganese and up to zinc. All these transition metal atoms consist of 9 valence shell atomic orbital. One is s orbitals, 3 is p orbital and 5 d orbital. Now we make a selection of 6 atomic orbital which may overlap along x-axis with group ligand sigma orbital to form 6 molecular orbitals. Remember, in all these orbitals, those orbitals will take part in bonding whose lobes is on x-axis. And those orbitals whose lobes is present between axes can't participate in bonding, and these orbitals are called non-bonding molecular orbital. In ligand field theory, s orbital transforms as a A1G. In ligand field theory, we call s orbital as a A1G. What do you mean by A1G? G stands for Gerard. This is the S subshell, and S subshell consists of positive sign which distributes equally throughout this sphere. Consider this is like a ball. Gerard means if we divide this spherical ball, this S subshell into two parts, then this part will be similar to the second part. The charge which is present in this part will be similar to this part. So this is Gerard. Gerard means if we divide a body into two equal parts, the one part will be similar to the second part. The charge that is present in this part will be similar to the charge present in this part. Since pore S orbital has same sign in all direction, in group ligand orbitals, all the positive lobe of ligand orbital in center, this red sphere indicates S subshell. On the x-axis, the ligand approach along the x-axis. So this pink color ball indicates the ligands. Positive charge equally distribute throughout the sphere, and all the lobe of positive lobe of ligands will approach along the x-axis toward the S subshell. The wave function of all six ligand orbital used for combination with pore S orbital have the same sign, that is positive sign, as the metal pore S orbital. So it causes maximum overlap. That's why the more overlap, the more will be the stability, the less will be the energy of S orbital. That's why in MOT diagram or in ligand field theory, the energy of S subshell is lower in all orbital because of maximum overlap, because of same sign. In ligand field theory, the three orbital of p subshell are called T1U. In T1U, U represent ungerard. What is ungerard? This is the orbital of p subshell. In this orbital, two lobes consist. If we divide this orbital into two parts, then the one part is not similar to the second part. In one part or in this lobe, positive sign is present and this negative sign is present. So this is ungerard. If one part is not similar to another part, then we called it ungerard. Each of the metal p orbital combined with the combination of ligand orbital involving two ligands. Here positive lobe of ligand approach and here negative. So two type of ligand involved in this combination. Remember, in pre-metal ion, all the orbitals of d subshell are degenerate, having same energy. But on approaching the ligand toward pre-metal ion, the energy of all the orbital in d subshell become change, and it splits into two groups in octahedral and tetrahedral complex, and it splits into four groups on the basis of difference in energy in scalar planar complex. These two orbitals of d subshell are called EG. EG means doubly degenerate group of orbitals. The energy of these two in octahedral complex become high because its lobes are present along x-axis, and it participates in bonding, and the ligand approach along x-axis. That's why, due to inter-electronic repulsion, the energy of these orbitals become high. This is dx square minus y square orbital. This is dz square. Remember, dx square minus y square orbital consists of dx square minus y square, the ligand approach along x-axis, and its lobes are present along x-axis, and dz square, the size of lobe is greater than the size of single orbital. Here it consists of positive sign in upper and lower lobe and the negative sign in this ring. This ring indicates the another orbital of dz. So the ligand of negative signs approach toward this ring, and the positive lobe ligand approach toward the upper lobe and lower lobe of dz square. In ligand field theory, dxy, dyz, dxz is called T2G subset, triply degenerate subset, a group of three orbitals which have same energy, and G indicates Gerard. T2G set have lobes directed between the bonding x-axis, and thus will yield no overlap with ligand orbital. This red line indicates y-axis, this indicates x-axis. The lobes of these orbitals present between x-axis. That's why these orbitals are called non-bonding orbital, and it can't participate in sigma bonding. How ligand field theory explains the tetrahedral complex. In tetrahedral complex, there are four ligands attached to central atom. The d orbital splits into two different energy levels. This is the pipe orbital of d subshells, whose energy are degenerate same. When ligand approach toward these orbital, it splits into two groups. The upper is called T2G and the lower is called EG. In case of tetrahedral complex, the energy of T2G become high due to approaching ligand due to inter-electronic repulsion, while the energy of Eg become less as compared to T2g and as compared to degenerate orbital of pre-metal ion. The distance between these Eg and T2g, or the difference between Eg and T2g, is represented by crystal field splitting del naught. Why the energy of this T2g become high? Consider a cube-like structure in which three axes are present. So the axis comes the ligands e.g. the ligands the lobes of orbital which are present on x-axis are e.g. is directed toward the face, while the lobes which are present between x-axis is directed toward the corner, that is the ligand approach toward the corner. The lobes of T2g orbital experience greater energy, that's why the energy of this orbital become high. The bottom two consist of dx square minus y square and dz square orbital. In octahedral complex, 6 ligands attached to the central transition metal atom. This is 5 degenerate orbital of d subshell. This is T2g consists of dxy, dyz, dzx. This is consist of Eg. Eg consists of dx square minus y square and dz square. Remember, the energy of T2g is less than pre-metal ion and then Eg. Why? Because its lobes are present between x-axis and the ligand comes along x-axis. The Eg experience greater energy due to its lobe present on x-axis and the ligand approach along x-axis, and due to inter-electronic repulsion, the energy of Eg become high and that of T2g become less. In square planar complex, the d subshell orbital splits into 4 groups. The energy of dx square minus y square become high in all orbitals. Then dxy, dz square, dzx and dyz. Why the energy of dx square become high? Because ligand approach along x-axis and y-axis and its lobes are present along x-axis and y-axis. That is, it experience greater inter-electronic repulsion. dz square and the lobe of dz square present on zx axis, so there is no ligand along zx axis. That's why the energy of dz square or dyz or dzx is less than dx square minus y square.